In our last example, we found that the general solution of y prime equals negative 5, 2, 1, negative 4 times y in terms of constants c1 and c2 are given by y of t equals c1 times e to the negative 3t times 1, 1 plus c2 e to the negative 6t times negative 2, 1. Let's sketch the phase portrait using the general solution that we found. The straight line solutions are scalar multiples of our eigenvectors v1 equals 1, 1 and v2 equals negative 2, 1. So we'll start our phase portrait with those. Now since e to the negative 3t and e to the negative 6t go to 0, these straight line solutions are going to be moving into the origin because we'll get smaller and smaller scalar multiples of our vectors v1 and v2. We'll indicate this with arrows pointing into the origin. But as we did in the last two phase portraits, let's consider what happens to the curves of solutions where c1 and c2 are not equal to 0. So we'll start with some generic point and look at what happens as t increases to infinity. As t goes to infinity, our function y of t is going to go to the 0 vector as a smaller and smaller sum of v1 and v2. This is because our scalar multiples e to the negative 3t and e to the negative 6t are both going to 0 as t increases. So we know that our solutions are going to be going into the origin. But we need to figure out how they approach the origin. Since e to the negative 6t is decreasing faster than e to the negative 3t, our scalar multiple of v1, so our term containing v1 will become the dominant term. So for large values of t, the term c2 e to the negative 6t times negative 2, 1 is negligible compared to the other term. And so near the origin, our function y of t approaches the vector 1, 1. That is, as y of t goes into the origin, it goes in asymptotically parallel to v1. What about in the other direction? What about when t goes to negative infinity? Here, both of our terms are going to be increasing. E to the negative 3t and e to the negative 6t will go off to infinity as t goes to negative infinity. So as t goes to negative infinity, we know that y of t moves away from the origin. And since e to the negative 6t will grow faster than e to the negative 3t as t goes to negative infinity, we have that the term c2 e to the negative 6t times negative 2, 1 will be our dominant term. And thus y of t will go out asymptotically parallel to v2. And as we've said in the other phase portraits, there was nothing special about the point we picked here. This can be true in any of our four regions bound by our straight line solutions. So what we see for all of our solutions is that they all come into the origin. For large negative values of t, the solution will be asymptotically parallel to v2, and for large values of t that are positive, our function y will come into the origin asymptotically parallel to v1.